Finding AN. Unknown radius 20. The following procedure may be used to find the radius for large tanks, silos, or curved roofs as shown in figure 20:1. Formula. Radius equals the chord of half the arc squared divided by twice the height of the arc. R equals C squared, 2A. R equals radius C equals chord of half the arc A equals height of arc. The chord of the arc is found by laying out 2 points on the circle A and B and measure between the points. Figure 20:1 shows points A and B and shows a measurement of 12 feet 0. For ease of figuring, point A and B can be set at even spacing, i.e. 8, 10 feet, 12 feet, etc. This makes locating the center of the chord easier and facilitates finding the height of the arc. AO in figure 20:1 illustrates the center of the chord. The height of the arc is found by measuring at a right angle from the center of the chord of the arc to the outside of the circle. Line OD in figure 20:1 would be the height of the arc. Chord of half the arc is the measurement from point A to point D, which is the hypotenuse of the right triangle created by point A to point O and point O to point D as shown in figure 20:1. Using Pythagorean theorem, as discussed in chapter 1, we can find the value of the hypotenuse or the chord of half the arc. Using Pythagorean theorem, h equals square root a squared plus 0 to the power of 2. H equals hypotenuse or chord of half the arc, AD, A equals adjacent side, AO, O equals opposite side, OD. Substitute and solve. H equals square root 6 to the power of 2 plus 2 squared. H equals square root 36 plus 4. H equals square root 40. H equals 6.32. Chord of half the arc equals 6.325 feet. If the chord of half the arc can be measured as shown in figure 20:2, the radius can be determined without using Pythagorean theorem and applying the values directly to the formula. R equals C squared, 2AR equals radius C equals chord of half the arc A equals height of arc. Substitute and solve. R equals C squared, 2AR equals 39.5 to the power of 2, 2 by 16.25 R equals 1560.25, 32.5 R equals 48.0. Radius of the circle is 48 inches. AB equals chord of arc. O equals center point chord of arc. OD equals height of arc. AD equals chord of half the arc. The radius can be found of an existing pipe as shown in figure 20:3 by using the same procedure as outlined for the curved roof, figure 20:1, or the silo, figure 20:2. Example 1. Find the radius of an existing pipe if the chord of arc is 20, and the height of the arc is 3. If the chord of arc is 20 inches, AB, the center of the arc will be 10 inches, AO. Height of arc is 3 inches, 0 to 0. Chord of half the arc equals square root 10 to the power of 2 plus 3 to the power of 2. Chord of half the arc equals square root 100 plus 9. Chord of half the arc equals square root 109. Chord O, half the arc equals 10.44. R equals C squared, 2A. R equals 10.44 to the power of 2, 2 times 3. Radius equals 18.165 or equals 18 3/16. 2 by 3. Problem 1. Find the radius of a silo with the following dimensions. Chord of the arc is 4 feet 10 inches. Height of the arc is 5 feet 4 inches. It may be easier if you convert feet to inches, do the calculations and then convert back to feet and inches. The answer at the back of the book will solve the problem using feet and then inches. ALTERMATE methods. Another method of determining an unknown radius is to establish 2 chord of arc lines and locate the center of each chord. Lines are then established at right angles from the center of each chord. The intersection of these lines will be the center of the circle. The radius may then be found by measuring from this point to the outside of the circle as shown in figure 20:4. An alternate and purely trial and error method to determine the radius of an existing bend requires only a string and a piece of chalk, or other suitable marking device. The chalk is attached to one end of the string and a pivot point is found that will duplicate the shape of the bend. When this point is located, a complete circle is drawn. The radius can now be found by measuring from the pivot point to the outside edge of the circle as shown in figure 20:5. Bending pipe with larger than normal radius 21. Once the radius has been determined as outlined in chapter 20 or obtained from the job plans or prints, the layout for bending pipe that must conform to the walls of large grain silos, circular storage tanks, etc. is basically a segment layout calculated from the radius expressed in feet. Figure 21:1 shows a larger than normal radius bending job. The figure shows a storage tank that is 18 feet in diameter with rigid conduit running between two junction boxes. If the diameter of the tank is 18 feet, the radius will be 9 feet, 1/2 the diameter equals radius, as shown in figure 21-2. The radius of 9 feet will be used for calculating the spacing between the bend marks for segment bending the conduit. Regardless of the actual distance between the boxes, we must first calculate the developed length for a radius of 9 feet to determine the spacing between the bend marks. This spacing will then be typical for the entire length of the conduit run. Note: the formulas for segment layout are covered in detail in Chapter 15. To find the developed length or the amount of pipe that will be required to bend a given radius. Developed length equals radius by 1.57. First, convert any radius in feet to radius in inches. 9 inches by 12 inches equals 108. Developed length equals 108 by 1.57. Developed length equals 169.56. The developed length of 169.56 is the amount of conduit that will be required to bend a pipe with a 108 inches, 9-foot radius. The developed length can now be divided into segments for bending. Remember from our previous discussion on segment bending that the smaller the degree of bend, the smoother the radius will be. This is especially important with larger than normal radius bending if the finished pipe is to look right and conform well to the tank wall. Bending 50 per segment, shot, will give us the smooth appearance we want. The radius of 108, with a developed length of 169.56, will require 18 shots. 90 degrees divided by 5 degrees equals 18 shots. By dividing the developed length of 169.56 by 18, we get a spacing between bend marks of 169.56, 18 to 9.42, or equals 9 3/8. Referring back to figure 21-2, it is important to remember that the developed length only make up 1/4, a quarter, of the circumference of the storage tank. The actual pipe between the junction boxes is greater than 1/4 of the circumference of the tank. The actual distance can be measured to determine the total pipe required. The spacing between bend marks and degree of bend will be the same for the entire length of pipe required. For this problem we will assume the actual measurement between the boxes is 38 feet 9 7/8, or 465 7/8. By dividing this value of 465 7/8 by 120 inches, the nominal length for one stick of rigid conduit including the coupling, we get 3.88. This means that this job will require 4 sticks of rigid conduit. The only thing left to consider before starting the layout is the couplings that will be required to connect the pieces of pipe together. We cannot bend on the couplings, so the layout must be adjusted accordingly. If 9 3/8 is the spacing between the bend marks, we should have bend marks 4 11/16, 9 3/8, divided by 2, or approximately 4 3/4, on either side of the center of the couplings. This will probably require that one or more pieces of pipe will need to be cut and threaded to make the layout come out right. If the layout, however, comes within 1 inch or 1.5 of the desired measurement of the coupling, the marks can be adjusted to approximately the desired spacing without adversely affecting the total pipe job and thus eliminate the need for cutting and threading. Figure 21-3 illustrates the concept. The first pipe should be laid out with the first bend mark at 4 3/4, approximately half of 9 3/8. From the end of the pipe and the remaining marks placed 9 3/8 apart. This will give the conduit run the same smooth appearance from the junction box and at each coupling as shown in figure 21-4. To make the bends at the first few bend marks when using a hydraulic bender, screw a short piece of pipe on the end of the conduit you are bending so the conduit can be supported on the pivot shoe as shown in figure 21-5. This method can also be used when short stubs are required for regular radius segment bends. Note: be sure the coupling and the short piece of pipe are made up wrench tight when employing this technique to prevent damage to the threads. When bending larger than normal radius pipe with a Chicago style bender, the pipe will need to be removed from the bender and reversed for the last few bends. Decimal and metric equivalent of common fractions of an inch. Trigonometric table. EMT, rigid steel, rigid aluminum. IMC, PVC type A, PVC type 40, Schedule 40. PVC type 80, Schedule 80. Conduit spacing chart. This chart gives the center-to-center measurements for conduit layout. Locate the smallest conduit across the bottom line and then locate the larger conduit on the vertical line. The value shown is the center-to-center measurement of the conduits. To this value add the desired spacing between conduits. Example. Layout a 2.5 and a 3.5 conduit with 2 inches spacing. The center-to-center measurement is 3.438, as shown in the shaded area of the chart. Add 2 inches for spacing gives a center-to-center measurement of 5.438 or equals 5 7/16. This chart can also be used punching knockouts or any other job that requires center-to-center conduit measurements. Glossary. Arc. Any part of the circumference of a circle. Back-to-back. 2 90° bends in one conduit, usually with both stubs turned up on the same plane forming a U. Benders. Chicago. Style. A general term applied to all hand-ratcheted, frame-mounted benders. Hand benders. Benders having a full shoe that the pipe is formed around. Used for hand-bending EMT, IMC and rigid pipe. Hickey. A handheld bender with no bending shoe that is used to bend 1/2, 3/4, and 1 inch rigid conduit. Hotbox. A broad term used to describe head devices used to soften PVC. Pipe for bending. Hydraulic. A bender consisting of a hydraulic pump, hand or electric, ram assembly, frame, bending shoe, one-shot or segment, bending supports and pins. Use for bending larger sizes of conduit. Bending shoe. One-shot. A full 90° radius shoe used with hydraulic benders. Segment. A bending shoe with a very small radius intended to bend pipe in multiple bends or shots. Bending table. A table used for hydraulic benders. It has a movable pipe vise for securing the conduit during bending. Bite. Placing the bender or hickey on the conduit and bending a small amount of bend. Several small bends are used to complete a 90° bend. Circumference. The distance around a circle. Concentric bends. Pipe having a common center with increasing or decreasing radii. Chord of arc. A straight line joining the ends of an arc. A distance less than the diameter of a circle. Chord of half the arc. The length of a line if it was placed diagonally. Tram the edge of the chord of arc to the high point of the arc. Degrees per shot. The amount of bend in degrees a pipe is to be bent for EACHB bend mark of a segment bend. Develop length. The amount of straight pipe needed to bend a given radius. Diameter. The distance across the center of a circle. Dog leg. An unwanted alignment between bends of an offset or saddle that make the pipe look like a dog's hind leg. Also called a wow. Ductility. Ability for a material to be shaped or formed. Gain. The amount of pipe gained, saved, by bending on a radius and knot. Hickey. See benders. Kick. A bend off less than 90° placed in a conduit to change direction. Leg length. The length of pipe measure from the back of the bend. 90° bend. Any radius bend in a conduit that changes the direction of the pipe 90°. Number of bending shots. The number depends on the size of the radius and the smoothness required of the bend. OD size. Outside diameter of a pipe. Offset. 2 identical bends placed in a conduit to change direction or elevation of the pipe run. OO. A pipe bent wrong that can't be used. Usually thrown out or said to be put in the OO pile. Pivot shoes, pipe supports, castings formed to the shape of each conduit size and held in the bender frame by pins. Plunger. Ram. The rod in the hydraulic cylinder which is attached to the bending shoe and moves forward when hydraulic pressure is applied. Radius. The relative size of the bent portion of a pipe. Reference point. A mark used to locate the edge of an obstruction for bending saddles. Segment bend. Any bend formed by a series of bends of a few degrees each, rather than a single one-shot bend. Shot. One bend in a segment bend. Shrink. The amount of bent conduit reduces in total length after an offset is bent. Spring back. The amount of bent pipe tends to straighten after the bending force is removed. Start mark. A mark placed on the pipe to start a segment bend layout. The start mark is not a bend mark and is only used as a bend mark if final. Adjustment to the pipe requires more degree of bend without adding to the stub height. Stub. The distance from the back of the bend to the end of the conduit. Sweep. A 90° bend with a radius larger than a standard one-shot shoe. Take up, come back. The amount that must be subtracted from the desired stub length to make the pipe come out at the correct length. Wow, dog leg, hoop-de-doo. An improperly made bend where the conduit was not held secure and the bend is not aligned right. The term is also used to indicate a slight bend made by hand or over the knee for correction or direction change.